Hello students, it's Dr. Sansom here for your pre-lab lecture for our saponification experiment for Chem 107. In this experiment, we're going to ask you to focus on the process skill of management, which is essentially coordinating your group efforts to be most efficient and effective. So planning, organizing, directing, and coordinating among the group members as you're working in lab. One of the things we want you to be aware of for this lab is that it's going to take place over several days. So in class today, you'll do most of activity 1 up until step 7. And then in a few days, you'll complete the rest of activity 1, and then you need to wait another day before you do activity 2. So you should be able to accomplish all of this before we meet again next week, and the report will be due then. Also today during class, you're going to be doing 3 lab skills that you'll use during this experiment. So the first activity that you're going to be doing is actually synthesizing soap. And one of the goals that we have is for you to understand what's happening at the molecular level. So saponification is a reaction between a triglyceride. So this is an example of a triglyceride. It has this 3-legged molecule over here, which is the basis of glycerol. And then it has these fatty acid chains that are attached. So as the reaction happens, the sodium hydroxide is introduced. It essentially breaks this bond to the glycerol, replaces that with a hydroxide group, and then we're left with this long chain fatty acid, but it's in the carboxylate form. So it has this negatively charged COO- group on the end. Because of that, we'll often see it written with a sodium ion there just to balance the charge. Of course, when it's in water, these two things dissociate from each other. And so we'll often also just see this long chain with the charged group on the end. And when this is done, after all 3 of these fatty acids have been removed, we have glycerol, which has the 3 hydroxyl groups on those 3 positions. So this is the overall reaction, and you can just see a little bit more detail here that this is the place where we are breaking the bond, and it's replaced then with the OH group. And then we're going to get 3 of these long chain fatty acids. Sodium stearate is an example if we have stearic acid as our fatty acid. This is technically classified as a hydrolysis reaction because we're adding water across this bond. Activity 1 is considered a cold process. Because the vegetable oil is liquid at room temperature, we don't have to heat it up, and we're going to use 1 molar sodium hydroxide. When we mix together the vegetable oil and the sodium hydroxide, it creates an emulsion. So you'll actually see that sort of change in texture of the reaction mixture when you mix it up. When the reaction is done after 72 hours, we add salt. And the reason that we add salt is that it helps us to separate out the soap molecules from the rest of the mixture. The second part of the activity is analyzing the soap that you have made. So we're going to check several properties. One of those is pH, and pH is important because if we had a bunch of extra sodium hydroxide, for example, then we would expect the pH to be higher. Normally we want our soap to be between pH 7 and 9. What is actually happening at the molecular level? If this is our fatty acid here with this carboxylate ion at the end where we have COO- group, this part of the molecule is polar, so we sometimes call it the head, the polar head, and this part of the molecule is nonpolar, and we sometimes call that the tail. So polar or hydrophilic heads of the molecules and nonpolar or hydrophobic tails of the molecules. This means that the nonpolar part can interact with oil and dirt, which are also nonpolar, and the head, the polar head, can interact with water, and that allows it to stick to the dirt and wash away with water. When you're testing the pH, that's one of the skills that you're going to do in class. And when you're testing the pH, just make sure that you're using the pipette. You're not dipping the pH paper into the solution. One of the things that you'll be asked to distinguish between when you're looking at the final soap that you've created will be how bubbly or foamy or sudsy it is versus how much of it is getting used to wash away oil or dirt. So just a little anatomy lesson here on bubbles of soap. Inside of soap bubbles that you normally see, they're filled with air, and air is actually nonpolar. And then there's this tiny layer of water in between two layers of soap molecules where the polar heads are touching the water and the non-polar heads are facing the inside of the bubble with air and also the outside of the bubble with air. So when we see lots of bubbles, this makes foam or suds that we associate with soap. When the soap is actually working, the nonpolar tails, instead of being in contact with the air, are surrounding oil and dirt particles. And then these polar heads face outward and are in contact with the water. And this is called a micelle. And when this happens, it might make the solution cloudy, but it doesn't form suds or bubbles because the soap molecules essentially get used up surrounding the oil, so they can't make bubbles. One of the other things that you'll be testing is the effect of hard water. And hard water contains positively charged magnesium and calcium ions, and they are attracted to the negatively charged carboxylate group at the polar head of the soap. And when they bind together, it precipitates out of solution and it forms what we call soap scum, which is a solid. And because of this, hard water reduces the amount of soap that's available for suds and for making micelles because some of the soap actually precipitates out. It doesn't get to do its job. Oil also causes less foam because more micelles are formed versus bubbles. In lab today, as always, you should wear the appropriate PPE. This is especially true of the first part of this experiment where you'll be working with the sodium hydroxide. It is corrosive, and so in the event of contact with skin or eyes, you should wash the affected area with water for 15 minutes. Again, make sure you're wearing your goggles and gloves and apron so that you can avoid that in this experiment. That's everything for today. I hope you enjoy the lab and take a minute to take a whiff of your soap. I think you'll be surprised that what you've made actually smells like soap.